Thank you. Yeah, I'm Henrik. I'm from Square Enix Japan, and I'm going to talk about Final Fantasy 15, about modeling interactions for ambient NPCs using strips. And when I say strips, I don't mean planning. That's sort of the distinction here. In Final Fantasy 15, it's a game that will come out eventually. It's going to be an RPG. It's meant to be a fantasy based on reality. So it means we have this interesting mix of high fantasy and almost modern day city life thrown together into the same world. And our player is going to go onto a journey through that world. So what we want to do is to emphasize the differences between these places. In March, we released a demo called Episode Das K, which had more or less 3 hours of gameplay. It was a test for the technology, the game mechanics. It was fairly well received, and so we go ahead with the idea. We just need to reconfigure this. With the idea of the game and implement the cities of this world. And the main goal here is to convey the culture and the culture differences of these different places. And when you think of culture, you may think of architecture, of art, of music, of fashion. There was earlier a very nice talk about how to do that with PCG. But normally, your artists are concerned with that. Here, we take a different approach and say, culture is also very evident in how people interact with one another and how they interact with the environment. And that's where this technology should support our designers. So when we think on interacting with the environment, a very old concept used as far back as The Sims are smart objects. So we can place objects into the environment that emit information, such as I can reduce your hunger by 10, or I provide some food. And then attach some data to that object so that NPCs are enabled to interact with that. Say we're attaching animation, we're attaching state machines, sound, and whatever else is needed to basically perform that interaction with that object. That is really nice, because for every new object we place into the world, we don't need to touch the NPCs anymore. But when we have groups of objects, like say 2 chairs and a table, it gets a little bit fuzzy on how to model that as individual smart objects. Like the chairs, fair enough, or they provide maybe rest, but the table there, what does it exactly emit? Like it has a surface, or so that's a bit unclear. Further, we now haven't captured the relationship between these objects. And we want to place multiple NPCs there, somehow interacting with one another. We would typically use a state machine or behavior tree to model their behavior, but they are more or less geared towards single agent behavior, not so much towards interactivity. So we have a hard time answering questions like, is there someone sitting on that other chair? Is that guy talking? Can I talk now? Or where do I place my food? So in short, expressing temporal and causal relationships of actions of different actors is difficult in this way, using single agent behaviors. It's not impossible. We just had a talk around 2 o'clock, how they do it in EVE Online with behavior trees. And way earlier in 2009, Piloso showed at this very conference how specialized gate nodes in behavior trees can be used to achieve that. but it's sort of an extension of the original language. It's not built in. We can have a look at how that would sort of look like. If we want to model a conversation as a behavior tree, we have 3 actions: talking, listening, eating. And we put these gate nodes in there that basically count how many NPCs will utilize or are utilizing the corresponding subtree. And then can formulate conditions over them and say, okay, you can only talk if there is someone to talk to at all. Don't talk to yourself, that's kind of stupid. You can only listen if there's someone else that actually talks. And otherwise, you eat, essentially. So that works, kind of. But still leaves some questions unanswered. Like, to whom am I actually talking? Who am I listening to? That's unclear. And that question may seem insignificant, but the moment we want to do some head movement, it becomes very important. Where do we target that animation? Further, when these NPCs have significantly different behaviors and we still want to coordinate them, we would need to build like a very large behavior tree for both of them. That usually doesn't go over so well. Further, the question arises, how do we model fairness? How do we guarantee that every NPC in principle has a chance to talk at some point? How are we removing any kind of bias that might or might not be there? And what if we want to do something a little bit more complex, like say, after 2 persons talked, all of them laugh simultaneously, because maybe they just told each other a joke. So that's not really satisfying for us. So we took a step back and said, okay, what are actually the goals here? Well, we want to model interactions in a simple way, because, well, simple is good. We want coordination to be a first-order element of that language, should be in the foreground for the designer. And they should be able to look at the multi-agent perspective, not so much be concerned with what an individual is doing. And of course, we want to have something that enables us to reuse data so that we're not wasting a lot of time with the workflow and can adapt scripts to different kinds of environments. So what we did instead of behavior trees is, firstly, we go back to the smart objects and equip them with knowledge about multiple assets instead of just one asset. And we design scripts around Blackboard as the coordinating element. So agents then have the ability to communicate with each other via that Blackboard. The first part is fairly straightforward. Instead of saying that chair is smart and that chair too, we just say there is one invisible smart object that knows about both chairs, the table, a couple of scripts, some emitters, and thereby we can capture the relationship between these objects. It's very, very close to the Smart Zone approach that was recently published about in Game.ai Pro 2. Pretty much very similar. But where we diverge is on the scripting side, which would be the second step that we have. But for now, a short look back to the 2 chairs and the table. So that scene now looks much cleaner. We just have one smart location that has one interaction type, knows about 2 chairs and a table. So it's much clearer what this scene is actually meant to be. When we come to scripting, there are 2 foundations I want to quickly talk about. One is strips, and one are tuple spaces. Strips, Stanford Research Institute problem solver. I guess most of you guys know exactly what that is, so I don't want to spend too much time talking about it. But for the others, it's a symbolic language to describe a problem domain. especially geared towards planning, but not necessarily exclusively used for planning. It's the basis of goal-oriented action planning that was most recently used in a game, I think, in Shadow of Mordor. And it describes domains basically in terms of states, actions that lead from state to state, and some goal conditions that states should satisfy in the end. The whole approach is absolutely ancient. The first paper was published in 1971, so has been around for a long time. A quick example coming from academia is that we have an action description like this, where we say we have an action called pickup, to pick up an object X, and it has a precondition that has to be satisfied before we can execute this action. So, for example, that object should be on the table, it should be clear of anything, and I better don't hold anything in my hand. And once I pick that object up, I modify the state of the world. So now I'm holding it, it's no longer on the table, so I remove that information from the world, and I no longer consider it to be clear. So pretty straightforward, and now one could, for example, take multiple of these action descriptions, chain them together, and arrive at a desired state, and that is then called planning. Again, this is not what we're doing. Instead, we combine this with tuple spaces, which are basically just blackboards. Originally, they were developed for distributed systems in '85, so also pretty old. But if you strip away everything you need for the distributed system to work, so all the consistency semantics and the like, what you're left with is a set of tuples, so pairs, triples, quadruples, and so on, with a little API to manipulate that and to query that. It could look roughly like this. I have this cloudy tuple space with a couple of tuples in there saying that Joe has coffee and Bob is a friend of Joe, for example. We can manipulate that by adding some information, like Bob has coffee too. Yay, go Bob. Of course, we can also delete information and say, now that he has coffee, he no longer has any friends. That's just the way. This is where this wildcard operator comes in. We can just delete a bunch of information at the same time. Of course, we can also query this and ask, is Joe a friend of Sue? And yeah, that's actually, it says so right there, so that's true. We can also query a little bit more and ask, has Bob anything? If so, what's that? We would get back, yeah, that's the case, and that thing you're talking about, that's coffee. So it's a little bit more than just asking for a truth value here. For the programmers among you, conceptually, this is just an unordered multimap with an integer as key over tuples of a variant type. So pretty straightforward thing with some additional API to do tuple matching. And what we're doing here is that we combine these two techniques and say, okay, our strips rule set will now operate over tuple space instead of the actual word representation, such that each NPC can individually evaluate rules, and each rule can cause actions and have an effect on the tuple space. So with that, we go back to the two chairs and the table, and now we want to create a little script that gets NPCs to that place and make them talk to each other. So the first thing we need them to sit down. So we have an action called sit. This action actually identifies a state machine or behavior tree. So it can be fairly complex. In fact, this very action will do path planning, it will do steering, it will figure out where to be in relationship to the chair when triggering the sit-down animation. So there can actually be quite a lot going on under the hood. And while that all is going on, we consider the NPC to be blocked. That is, we are not evaluating any other rules for him. Now, we need an object to sit on. And ideally, that's a chair. So we write that down in the precondition. And this information has been pushed by the SmartLocation that knows about the chairs into the tuple space. So it's there. And this would actually work, but it's not quite what we want. Our NPCs are a little bit more lazy. They tend to choose the closest chair. So we write that down and say, OK, give me the closest chair with respect to myself. So we have two more built-in symbols here that basically resolve the function pointers. One will sort solutions for us according to a distance, and the other one refers to the currently evaluating NPC, me. So that's nice, but still not quite what we need. We need to make sure that there is actually no one sitting on that chair. Furthermore, we need to make sure that no one has the intent of sitting there. So what we need is a reservation system. Let's just write that down. That chair thing X should not be reserved by anyone. And the keyword reserved is actually, at this point, not defined. It's a completely new symbol. It's just an integer, a key into the tuple space. And its meaning will be defined by these rules. So the moment I trigger this action of sitting, I say, OK, now that thing is reserved. I add that information to the tuple space. That's pretty nice. We then need a little bit more information to get things going. And we would like to be able to say, after that action has been completed, inform other NPCs to say, OK, now your stance has changed. And you're now sitting. And furthermore, maybe push a timestamp to the tuple space to say, OK, in 10 to 15 minutes, maybe it's time to get up again, so that the scene has a certain dynamic and NPCs are not sitting there forever. Need some movement. This little term over here that gives us a timestamp in the future will be evaluated immediately when it's needed. In this language, we don't have any kind of term manipulation as opposed to like classical declarative languages. But this makes it also way simpler and way faster to handle at runtime. OK, that leaves one more thing. We would then like to switch the state of the NPC and say he's now sitting. This is basically a little syntactic sugar trick to keep preconditions smaller and to separate rules into states. It's just, yeah, syntactic sugar, basically. OK, now NPCs should sit in principle. What we need is talking. And here we can exploit the fact that a rule does not necessarily need to trigger an action. It can also just operate over the blackboard. So we can formulate that any NPC who's sitting and who does not see a designated talker in the blackboard, so talker is false, can designate one by saying, we're taking a random sitting NPC. Any here is a keyword that will give me a randomized participant in that little script. Take that guy and designate him as talker. And then a second rule can say, OK, if you're the one who has been designated in that way, and there is someone else also sitting, then you can talk to him. Once you're done with that, remove that information about the designated talker so that the previous rule can grab again and define another NPC to talk. That leaves one thing that we need to do. We need NPCs to do some listening motion, some nodding. So we just write that down and say, okay, listen if there is someone talking who's not you, because that's polite. So in total, we now have 4 little rules. Let's see what that looks like, and I hope, yeah. So our NPCs are sitting down on their chairs. The script finds an NPC to talk to talk. The other guy is doing some head motion. And after that little action has terminated, the script will randomly determine another NPC. In this case, it happened to be the right one. So for rules, it's actually kind of nice. Here you see the debug UI. In green are rules that are currently active, so the listening and talking usually, and in yellow, occasionally flashing a rule that just fired. So what happens when we now spawn a third character in this scene? Well, he'll get information from the SmartLocation. He can join the script, execute the first rule, and go to the closest unreserved chair, sit down, and because there's currently someone talking, we'll get into his listening animation, and when that talking animation has finished, he'll be considered to be the talker. So what we just did is a little script that can deal with 2 NPCs, 3 NPCs, 4, 5, 6, can scale it up, but eventually, of course, it's a little bit awkward if you say that in a large crowd, there's just one person talking. That never happens, right? And the script can even dynamically adapt itself to the number of NPCs. So that's neat, but we want to do a little bit more. We now want to be able to say, okay, these guys should be able to order some food from a waiter and then continue the discussion over some food. A waiter sort of calls for the concept of roles. A role is just a simple trick to say, okay, our NPCs have different purposes and different capabilities. So we can annotate the script with some information about roles and say, it needs up to 3 customers. I just came up with that number quite randomly. And up to 1 waiter, also completely randomly chosen. Most importantly here is that we don't necessarily need a waiter. If there is none, we can still run the script. They will just not order anything. Vice versa, we don't necessarily need customers. If there is none, well, the waiter will just be bored and idle around. That's okay. In this third column here, dynamic join, that's just a little flag to say, can NPCs join that script, that row on the fly while it's running? So the little scene we just had, the previous video, the third guy joined the script dynamically. And sometimes we don't want that. If we set that to false, we actually would express a culture that's a little bit less social. Like, people will never join other people at a table. So we have a little bit of expressiveness here. Well, you talk about roles. You probably also need to talk about role allocation, the process of finding out which NPC is going to do which role. And that is an NP hard problem, at least in the formulation that I just gave you. But in games, typically, the problems we face are trivial. They're really simple. So when it comes to role allocation, there are very hard problems in games. So we can get away with a greedy approach, which would just basically first satisfy all minimal cardinalities for the different roles, and then see if it can add any optional actors to that script. Because it doesn't actually need to assign a role or a task to every available actor. The remaining ones can just go their merry way, and it's fine. So basically, in each iteration, we just assign one actor to a role until we're either satisfied or have a failure case. So there is no search whatsoever. We can guide that, though, a little bit with a heuristic and say, try to satisfy tasks with the least remaining options first, and use actors with the least amount of options first. Will allow us to solve a couple more problems that way. Of course, in the end, it is NP hard, so that strategy will not always find a solution, which is completely fine. We just randomize the input, and if we fail, we fail. We can try again next frame, we can try again in a couple of seconds, can even try again in a couple of minutes. We don't need that script to run right now. So with that, we can get our waiter into the script, and now I might scare you a little bit because that looks so complicated. Now I want to briefly talk about a few of the language idioms we get from that. Firstly, we now add the ability to filter NPCs by role to rules. So this little action here is a wave where the customer says, "Hi, waiter, I want to order." And obviously, that should only be executed by a customer. It's also more or less syntactic sugar. But more importantly here, we can actually, with that wave or that bark action, communicate information via the blackboard and say, me here at this table, I want to order something. Further, with this little trick involving these three occurrences of waving, which also is just a newly introduced symbol, we ensure that only one actor at a time will execute this action by adding it to the tuple space before we execute the action and removing it again after. That just looks better that way. And finally, we can query, of course, for a waiter, for an NPC that has the role waiter, then we can do some selection over them. Like, for example, check some simple geometric relationships, like in front of. So these two predicates here will select a waiter that is in front of the evaluating NPC. And by that, the script will actually select a pair of customer and waiter, such that the customer can essentially see that waiter. So then, of course, the waiter should react to that. We say, okay, if there is an order up at some table by someone, then please go to that table and switch your state to take order. I won't go into any more details about how to model that precise scene. It's a little bit besides the point. Let's just watch it. So again, our NPCs are sitting down, and the left one is now executing his waving motion to a waiter that is waiting off screen. In the meantime, they continue their talking motions until the waiter arrives and takes individual orders from each of these NPCs. And every single one of these talking actions to the waiter actually communicates information about that they want to order, and in principle could also carry information about what they want to order. Now, waiter moves off to the bar to fetch beverages and stuff, and conversation continues again. So like the basic of the script is still running. And eventually, waiter comes back and brings us some hot coffee and some stuff. And of course, eventually you run out of animations, and you need to trick things a little bit and teleport stuff around. But this is ambient, so that's fine. Yeah, this little scene takes someone who is familiar with the system maybe 2 to 3 hours to get running in this way. So yeah, that's basically what you get out of the system. Now let's have a little look at the system itself. There are 3 parts I quickly want to mention: how we start a script, how we execute a script, and how we execute different rules. There's really not much to it. Starting a script is basically the emitter of a SmartLocation, which will query with a very low frequency your favorite spatial database, so every few seconds. Filter out any NPCs that are otherwise busy. Choose an applicable script, do role allocation, and if that happens to fail, we try to find a different script that matches the current composition until we're done. And here you can do a little trick and keep track of basically what's your least recently used script and try to improve the variety of the scripts that are actually being played. Once you start a script, we execute it, of course. And the main point here, and this is surprisingly important, is to shuffle the participants in each tick, because that will remove any kind of bias that you unintentionally have due to the ordering in what essentially is an array. After that, we apply the deferred post effects, if any action finished. And then we apply the rules. Rule application is basically also very straightforward. For each participant who's not executing an action, we use its state to index into the array of rules, and then go through these rules and find the first one that matches both the rule and has a valid precondition. The first one we find, we trigger the action, apply the post effect, and mark the participant as executing. So really very, very straightforward. The only thing that is a little bit more complicated is the evaluation of the precondition, because that's a backtracking search. So let me show you a little example. Take this incredibly boring looking formula, P of A and B and B larger than A plus 2. I tried to come up with something interesting, but this will do. So firstly, we initialize a couple of data structures on the stack. We need an array to hold arguments to predicates, and here the largest number of arguments is 2, so that array has 2 elements. And we need an array that holds our evaluation state. That is the values that we assign to variables, plus a little integer that keeps track of where in the backtracking search we are. Once we have that, we can start by evaluating the leftmost predicate. Firstly, we evaluate the arguments. And these are currently unassigned. And here just wrote null to say they don't have a value. In case of P, we now look up a matching tuple in the tuple space. Write that to the argument array. And for example, this could be 5 and 6. We write it back to the next state. So A becomes 5 and B becomes 6. We increment, go to the next predicate, evaluate the arguments again. So argument 1 is B and argument 2 is A plus 2. The result is, of course, false. So otherwise, that example would be a little bit too boring. So we backtrack, and that just means we decrement our state, and we increment the choice to wherever we get to. And then we try again. We evaluate the arguments, we evaluate the predicate, and we might get back 1 and 4 in this case. We write it back to the state, increment, check the next predicate, evaluate the arguments, check the next predicate. So is 4 larger than 3? Hell yes. So we write it back to the next state, increment, and we're done. The main point here is that we're just going back and forth over a little array on the stack. So this is quite fast. What we also want to be fast at is the build chain. So the tools and the iteration times the designer have. And that includes the editor, the compiler, and any kind of runtime debugging. So for the editor, we chose a tool that looks like this. Some people might roll their eyes, but our designers are very, very happy with that tool. They know it. They're comfortable in it. And if we look at the example conversation that I initially showed you, those 4 rules, plus an additional rules to terminate things, this would be the corresponding representation with one row per rule. And actually kind of compact, kind of nice. So we can read and write XML, so that makes it very easy to integrate into any existing chain. And with a few hundred lines of Python code, you can actually watch the designer saving a file, then call the compiler and propagate the error right back into the tool and put a little comment there and color a cell and the like. They were very happy with that. Speaking of the compiler, that guy just takes the XML input, parses it, uses a little Nucl.ai formula parser for the more complex terms, builds an intermittent model that we use for validation, and then plops out a binary plus some debug symbol or table for populating a debugger. And the keyword here is validation, which is very, very important if you want to keep iteration times short. The earlier we can detect an error, the better. And we have a formal model, so we have many opportunities to reason over any kind of errors. It strips. We could plan as a validation step. We're not currently doing that, but it's sort of on the to-do list. Otherwise, what we did is we added some mode declarations, so the compiler knows about the expected flow of information from predicate to predicate, and can then check things like whether or not a predicate can ever become true, whether or not variables are grounded when they're required to be so. You can check whether actions have their essential parameters. You can check whether states are reachable, to a certain degree, at least, and whether rules are reachable. Of course, we can't find anything. We can't find all the problems, because this is actually Turing complete. So, yeah, you need runtime debugging. And this is how our UI in the game looks like for that. We can look at the rules, we can pause a script, we can inspect a script, we can step through it, we can look at the tuple space and so on. So pretty much the normal stuff. So to conclude, I showed you a rule-based alternative to finite state machines and behavior trees. It's geared towards coordinating multiple NPCs. And it does coordination by data, not by structure. So if you want to coordinate an army using a hierarchical approach where you have squads and groups and the like, is probably a better approach. This is more designed for ad hoc cooperation between characters. Our designers, when I asked them what they think of this, they said, it has a more natural viewport than our state-driven visual scripting. So that's good. It has a high degree of freedom to create what we want to create. That's also good. It has a steep learning curve. Yeah, that's sort of the curse of any declarative approach, I'm feeling. But it's true. And finally, it requires some effort to write the script, even if you want to do just simple one-shot things. That is also true to a certain degree. But then again, if you want a character to just lean against the wall and never do anything else, you don't really need AI for that. So to summarize, it's a very expressive system. It gives you quick results. It's scalable. Its relationship to planning allows for on- and offline reasoning. It has a steep learning curve. It's initially confusing. And the readability when scripts get larger is not that particularly great, admittedly. But then if you look at a large behavior tree or a large state machine, I don't personally find them very readable either. That's maybe something that we need to work on. In terms of Final Fantasy 15, we can now express cultures by means of interactions. We enable designers to do so. We have adaptive scripts that simplify the production, so it's a win. And in the future, what is basically left is to, well, finish the game. Deliver the culturally interesting cities of that game. And for me personally, and on the research side, planning as a validation step and also to do more online adaptation is something that I really want to do. So with that, I want to conclude with just a little video from that apparently has audio from the demo we released in. Thank you. That's so kind. From the demo that we released in March. And basically, all the characters here are completely under control of smart locations and the corresponding scripts. So yeah, thank you very much for your attention. And if you have questions, I'm all ears.
You mentioned that you're treating this as a very research-oriented problem, and it sounds like you've got a fairly academic background as well. I was wondering if you're planning on releasing any white papers or anything that we could read once, obviously, Final Fantasy has been released or close to release.
That actually is a very good question. I would need to clear that up. It's a very nice idea, but I need to talk with the powers that be for that.
So very nice talk. One question was, how do you handle interruption of the dialogues? Like when you see in the example you show, when the guys are just first talking and then they order, do you mark the asset to know like this is a good moment in which I can interrupt my dialogue and then I can order and then come back? And also what happens if the player can interact with them?
Yeah, that's something that I didn't really show in this talk. We have additional rules, sort of special rules that can interrupt an action. Because usually an action is considered to be blocking, and that assumption makes the script very simple, and that's why I like to keep it. But for the special cases where you want to really cut an action, you have these special rules. In case of the player, we can also terminate the whole script, basically.
Perhaps, yeah, I guess you already answered it, but basically it was about how robust it is to player interactions coming from the stream.
Sorry, what?
How robust your system is to player interaction. How can you handle... Curious how reactive the system is to player interactions. How do you handle situations where player blocks potential actions?
I'm not quite sure I'm understanding the question correctly, but whether or not a player can
yeah, I mean,
interact.
I guess the player can block something happening? I mean, if it takes a share or something like that. So how will it handle that?
Very short answer, yes. We are able to represent the player in these scripts, and he can basically act as if he were an NPC in them by pushing some buttons.
Hi. Is there any way how you manage the integrity of the tuple space?
Yeah, we do some safety checks. Like we don't allow duplicates. We don't allow things to overgrow. And there are a couple of checks that make sure that the backtracking search does not get stuck in a loop or something like that. Other than that, no. The tuple space is guaranteed to be completely cleaned up once the script terminates. So we're not that worried.
Hi, thank you for your talk. I was wondering, since it seems pretty random, the people talking around the table based on the script, do you have like a special work done to have like coherent dialogues between the various ambient life, or?
To have what?
So do they, when they speak, do they have like a coherent dialogues because they are like speaking randomly, I guess? So,
no, there's no actual dialogue behind this. This is just for ambient background stuff. Though we might or might not do something about that.
Okay, I think it's been a long day, so it's time to call it an end. So thank you very much for your talk.